Hello everyone. So again, welcome back to the latest lecture session, right? So a quick recap of what we have been up to. So in the context of remediating contaminated soil or sediment, let's say, we were looking at in situ chemical oxidation methods, right? And in that context, we were looking at a particular case, let's say, or particular site, rather, which was contaminated with tetrachloro or perchloroethylene, let's say, right? Tetrachloroethylene. And in that context, we saw that, let's say, there were two sources. As in, one source was that, let's say, there was one particular spill event where relatively larger volume of the relevant solvent spilt over and soil was contaminated, and this particular contaminant was transported through the storm water drains too, right? That was one way aspect, but that was a one time spill. And the second one was due to, let's say, miscellaneous spills or small spills occurring daily, and these spills typically were washed into the sanitary sewers, and there was a leakage at one particular junction of this particular sanitary sewer network, let's say, and we saw that there was considerable contamination of the relevant groundwater, let's say. So obviously, if this groundwater is contaminated with PCE, you will also know, or obviously know, that typically soil will also be contaminated because this is a hydrophobic compound, right? So that's something to keep in mind. Also, we looked at the different profiles. I think we saw that there is an impermeable layer 18 feet from the surface, right, relatively impermeable layer, and I believe we also saw that the hydraulic conductivity was typically high around, let's say, 10 feet from the surface, right, and this was some such profile, I guess, right. We are going to look at these aspects again, right, and the other aspect was that PCE, let's say, would also naturally be degraded, let's say, in the soil, let's say, or in the environment, but obviously at much slower rates. And I believe people also detected trichloroethylene, 1,2-DCE, let's say, and also vinyl chloride, right. These are all the byproducts of PCE, let's say, right. So this is what they were using initially, but they detected all these compounds, right. So and then we saw that for this particular plume, the groundwater was moving in this direction, and thus the shape, let's say, right. So this was the shape, and they looked at different soil, groundwater, and so on sampling locations, or samples, pardon me, right, for transects and so on. We looked at these in general. So let's move on to the next particular aspect, let's say, right. And again, keep in mind that took, I believe, soil samples along with 6 transects, T0 to T6, right, T0 to T6, right. And so they were trying to capture the profile along the axis and also perpendicular to the axis too, right. So that's what they were trying to do, and I believe here we have a picture of the relevant soil core sampling, let's say, right. This is the equipment they used, and I guess these are these transects that we looked at, let's say, right. And let's move on, right. Retrieving soil cores, again this is a geoprobe, that's something we also looked at, let's say, even for pumping the relevant oxidant into the relevant soil, right. So again, TOC concentration, so why is this important now? So soil, let's say, will have some fraction of organic compounds, let's say, right. So these organic compounds obviously will be able to absorb hydrophobic compounds, right, and all these 4 compounds that we have looked at, let's say, are remarkably hydrophobic. Some of them are also pretty volatile, let's say, and these particular contaminants will be adsorbed onto the organic fraction of the relevant soil now, right. So you are going to have contamination of the groundwater and also contamination of the soil. So obviously you need to look at those 2 aspects, but to be able to get an estimate about the amount of contaminant that's going to be adsorbed onto soil, you obviously need the total organic carbon concentration. Typically you have the TOC test that you can do. So let's look at what we have out here. So this is the depth below the ground surface, let's say, from -7 to -16, around 16 or so. As we know, we have a clay layer, a relatively impermeable layer, let's say, and as you see the general trend, I guess they are trying to approximate by a linear relationship, but it doesn't, there is no particular relationship here, but certainly you can see that there is an increasing trend, as we go deeper or further away from the surface, let's say, what do you see? We see that the TOC concentration, or the fraction of organic carbon in your soil, let's say, is increasing now, right. So what does that mean, let's say, or what does that how does that affect this particular remediation, let's say, or remediation of this particular site, pardon me, that now, let's say, if the relevant contaminant, has permeated through to the lower reaches, let's say these reaches, let's say, right, What does that mean? You know, most of it or considerable fractions of the relevant contaminant would be adsorbed onto soil, and it would typically be considerably difficult to relatively degrade that particular or remediate that particular soil, let us say, right. So, let us look at it. You know, here we looked at the generic values. So, different transects, right, this is along the direction of the flow of groundwater, right. So, between 8 to 12 feet, this is the fraction of TOC, let us say, or percentage of TOC, and as you can see, they analyze many samples. It is not only from 1 or 2 samples, as we discussed multiple times during the course, I guess, right. Now, you need to get your site characterization done pretty well, right, or you need to characterize your site pretty well. Otherwise, obviously, if you try to, what do we say, limit your resources when trying to characterize the site, let us say, you are more or less a blind man walking out there, right. So, again, as you can see, they spent considerable time and resources here, and as you see, typically, let us say, in relatively shallow or mid-level regions, the TOC concentration is more or less around 0.1 or 0.11%, right, and in the lower reaches, it is almost double, right. So, that is a remarkably high or considerable increase out there, right. So, that is something to keep in mind now, right. So, let us move on. So, again, but one aspect looks like is that, you know, there is no distinct what do we say, high organic layer out there, as in there is no one distinct organic layer, let us say, you know, high what do we say, layer of soil that has high organic content, let us say. That is something to keep in mind, let us say. General trend, right, that is something that we looked at, and they mentioned that, let us say, after or about 16 feet below the ground surface, an abundance of organic materials such as wood and peat was below this contaminated zone, right. Again, if this particular contaminant had been allowed to, let us say, permeate further down, let us say, it would have been absorbed by, you know, this particular high organic content soil, let us say, right. That is again something to keep in mind, let us say, right. So, concentration of metals and sulfur, why is this important now? So, let us look at some of the relevant agents here, I guess. Here we have manganese, and as we see here, as we go down or away from the relevant surface, let us say, the surface is somewhere out here. So, this is 8 feet below surface, 9 and so on. You typically see that the manganese concentration is increasing here, right, and it is maybe maximum of around 100 milligram per kg now, right. So, let us look at the other more important case. So, here as you can see, here we are looking at iron, and here it is Fe2 plus or the ferrous iron typically, let us say, right. And as you can see, again the same trend, as in as you go down, let us say, or away from the surface of the soil, you see that the iron concentration is typically increasing now, right. So, that is what you see here. But keep in mind that here the scale is different, as in the maximum iron concentration, let us say, is around 10,000 milligrams of ferrous iron per kg of soil, and here it is around here, as in for manganese, it is around 100 milligrams of manganese per kg of soil, right. So, why is this relevant, let us say, as in why is the concentration of ferrous iron relevant now, right, because ferrous iron is a reducing agent, let us say, right. It is an electron donor now, right. So, as in it can give out an electron, let us say, and let us say what do we say, release or electron and produce Fe3 plus, let us say, right, or be oxidized to Fe3 plus. So, that is what we have here, Fe2 plus going to Fe3 plus plus 1 electron, let us say, right. So, this is what can happen or occur out there, right. This is one particular half reaction, but as you know, let us say, I think for permanganate, I mean obviously I am not going to write the relevant what is it now, relevant balanced half reaction, but we looked at that earlier, and some relevant other variables here, right. I am just writing the generic case. We saw that permanganate, let us say, is an electron acceptor, right, as we can see here, it can accept electrons and be reduced to MnO2, this solid phase, let us say, and obviously you had either H plus or OH minus and so on and so forth here, right. So, again the key aspect is that MnO4 minus accepts electron, it is an oxidant, right, or it is an oxidizing agent, but here you have ferrous at very high concentrations, let us say, or considerably high concentrations, let us say, and that is an electron donor. So, thus you will have a redox reaction out there, right, and this Fe2 plus will reduce MnO4 minus, or you can even say MnO4 minus will oxidize Fe2 plus. So, more or less the net effect is that some of the MnO4 minus or permanganate that you are going to put into the soil is not going to target the relevant contaminants, but is going to be consumed by the ferrous iron, which is at considerable concentration in the relevant soil, right. So, that obviously needs to be taken into account, right. So, that is what we have out here. So, let us move on, and then again sulfur concentration typically only in reducing conditions, let us say, but again similar trend as in with decreasing or as we move away from the relevant surface, you see increasing concentrations, let us say, right. So, that just adds to the complexity of your relevant problem here, right. So, let us move on. So, conceptual model of permanganate injection though, right. So, here this is the side view, obviously, this is the side view. So, here is the groundwater table, this is the surface, right, and groundwater flow direction, yes. So, here we have the this particular legend tells us that this purple colored slots are the permanganate injection points, let us say. As you see, they injected it at multiple depths, right, at around 6, 9, 12 and maybe 14 feet below the ground surface, and also in along different locations along the groundwater flow, right. That is what you see out here. And then obviously you see the different monitoring locations too, right. Keep in mind that we are not going to just pump everything in at one particular location. We will identify relevant locations and pump different oxidant doses depending upon that particular local concentration, let us say, and the relevant oxidant demand. We are going to pump the relevant what do we say, oxidant into that particular injection site, let us say, right. So, that is what we have here, and here we have the top view, right, and here you see that this is the source more or less, right, and these are the different transects, I believe, right, and here they are, you have the permanganate injection transect, let us say. That is what you see out here, again nothing but your particular injection points out here, right. That is what you have here, plan view and side view here, right. So, again as you can see, you have what do we say, in series different transects for soil sampling and obviously for injection of permanganate and again for monitoring wells, let us see, right. So, just a relatively more complex system. So, well locations and names, again just wanted to convey the extent of what do we say, monitoring or injection wells located. So, here we have deep reflected by D and S reflected by shallow. This is the source of the contamination, let us say, this particular reference point. We are looking at this picture so that I can just convey the complexity of the system, let us say, right. And typically as we looked at earlier, to save on relevant aspects, let us say, they looked at clustered locations as in clustered sampling for both the shallow and the deep wells, let us say, right. That is why you see more or less similar profiles out here. Again let us move on. So, here we will come to the actual results, let us say. So, before oxidation, which is or before adding the permanganate, you have in February 2013, let us say, the CVOC, right, which includes PCE, TCE, DCE and vinyl chloride in this particular case, right. What is the profile here? So, in the shallow well one particular profile, and in the deep well, I guess in the deeper locations, let us say, one particular profile, right. So, more or less similar profiles, but slightly higher concentrations, let us say, at some locations in the shallow region, let us say, right. But as you see, still more or less the plumes shapes, let us say, and the concentrations, let us say, are relatively similar now, relatively similar, right. So, that is something to keep in mind. So, let us see what the scenario is after one injection, let us say. If you remember, the relevant permanganate was injected in or injected 3 times, let us say, right. And let us look at the scenario after the first injection, and as you can see, there is considerable improvement already, right, after the first injection itself. And keep in mind that initially they as in the relevant people who remediated the site only pumped it in as in the permanganate in the first shot anyway at a few locations, not all the locations, right. Typically in this region, that is where they put in the relevant what do we say, permanganate now, right. So, as you can see, there is considerable improvement out here, right. And also if you remember, they waited for around 2 months or so before they monitored the relevant data, let us say, right. As in, if I injected the relevant permanganate into the relevant soil or groundwater today, only after 1.5 months or 2 months did I or the relevant people monitor the relevant site. Why is that? Why not, let us say, tomorrow, or just try to look at, let us say, how much time permanganate will take to reduce these compounds, not reduce, pardon me, oxidize these compounds and look at it immediately, because here let us say the reactions are going to occur typically in the aqueous phase, right, typically let us say, right. And let us say now the relevant contaminant in the water has been consumed, let us say, or has been oxidized. What is going to happen now? The contaminant that is on the soil, let us say, is going to desorb into the relevant water now, right. So, you are going to have desorption and thus a rebound or increase in the concentration will be witnessed, let us say, right. So, to take that into account, typically you are going to give some time for the equilibrium to be reached, and that is one of the reasons, I guess, they as in the relevant people monitored the site after around 1.5 months or even more, let us say, after injecting the relevant oxidant, let us say, right. So, that is something to keep in mind. So, let us look at the case for post oxidation injection 2, let us say, right. So, as you see, this is it is getting better, as in especially earlier in the first injection, the deep well, it was still considerably contaminated, but you see now that not deep well, the deeper locations, let us say, were relatively contaminated, but you see now that it is getting better. But one aspect to keep in mind is that compared to the first injection, second injection was almost twice the amount of permanganate, and also they put up or injected the relevant permanganate at more number of locations, right. That is something to keep in mind. Anyway, that is something we covered earlier, right. So, let us move on. Again, this is after the third injection, right. So, now as you see, more or less within this particular shallow well region anyway, or shallow region, most of the relevant sites have been cleaned up, relatively cleaned up, right. But one aspect I would like to point out is that we are looking at total CVOCs, as in PCE plus TCE plus DCE plus VC, let us say, right. But typically the standards, let us say, based on the toxicity of the relevant compounds are set for individual compounds now. But because this was a pilot scale study and they wanted to look at the effects, let us say, while also remediating the sites, typically they have looked at total CVOCs, but it would have been a much better work, let us say, or it would have been worthwhile if the resources were available to monitor the concentrations of these particular individual toxic compounds too, and not just the total CVOCs. For example, we do not know, let us say, if most of the total CVOCs after the cleanup is just present as vinyl chloride, let us say, we do not know that. I am just giving out an example out here, right. So, to prevent those cases, let us say, it would be better, let us say, to also get some idea about the individual concentrations, right. Again, as you see though, from the point of view of total CVOCs, the situation is much better, right. And here we see this particular case, let us say, again this is the source, if you remember, again in the deeper locations, yes, it is much better, but maybe not complete cleanup. But again, let us say, if required, people can inject the relevant permanganate or the oxidant again, let us say. But again, this is the case for the pilot scale demonstration, let us say. But if you see this compared to the initial picture, this is much better though, right. So, this is pre-oxidation before the cleanup, and after post-oxidation after the third injection, let us say, right, pre and post after the third one. As you see now, there is a remarkable difference out here, right. So, same case with the deep wells, right. So, this is the case for the deep wells, not deep wells, pardon me, deep locations, let us say. This is pre or before injection of the oxidant, and this is after injection of the oxidant after the third case. This is something we looked at, but now you can compare and draw the relevant conclusions, I guess, right. So, that is something to keep in mind. So, let us keep moving. So, here we are also going to look at Cl minus concentrations. So, as we mentioned earlier, let us say one of the other indicators of, let us say, the degradation taking place is that your byproducts, let us say, from the relevant half reaction are going to be Cl minus, or is going to be Cl minus, let us say, right, because you have C2 Cl4, right, Cl, let us say. Obviously, once you oxidize this and you end up forming carbon dioxide, let us say, you are adding MnO4 minus to this particular matrix, let us say, one of which contains this PCE, which has 4 Cl minus. So, C carbon is going to be oxidized to CO2 and Cl minus is going to be released. So, what would you typically observe? You would typically observe an increase in Cl minus concentrations. So, let us just try to understand that. So, in the shallow region, let us say, or from the samples in the shallow wells, let us say, so this is the pre-oxidation concentration, but in the deep wells, even before oxidation, considerable concentrations of Cl minus existed, but this could be due to two reasons, as in by the time they started remediating or adding the relevant MnO4 minus, keep in mind that some level of degradation or natural degradation already took place. So, some Cl minus would have been released, or there could also have been sources of Cl minus in the relevant ground itself, right. But looking at the relevant concentrations, you can draw the relevant conclusions, as in is the Cl minus from the degradation of the compounds, or is there a localized source there. But again, something to keep in mind is that even before adding the oxidant you still have considerable levels of Cl minus, and let us see how it is going to change. Typically in the higher what do we say, or shallow region, you have relatively less Cl minus, and in the deeper locations you have relatively more Cl minus. Could this be due to the case that typically as you go further away from the relevant surface, or deeper into the ground, let us say, relatively more reducing conditions prevail, where let us say the degradation of PCE into TCE, vinyl chloride or DCE is more favorable. Could that be the case? We do not know, but based on that data, maybe that is one particular possibility, let us say, why the Cl minus concentration is higher in the deeper wells and relatively lower in the shallow regions, let us say, right. So let us move on. So post oxidation, let us see. So you see slight increases in this particular Cl minus concentration in the shallow regions. So this is the pre case, right, pre-oxidation injection, and as you can see, typically the, it increased out here, right, it as in the Cl minus concentration increased, right. Again, that is something to keep in mind, or that is expected. Why is that? Because Cl minus is one of your byproducts when you add your MnO4 minus to the relevant compounds, let us say, right. So again, even in the deeper regions, let us say, or in the deeper wells that were monitored, you see again an increase in the Cl minus concentration. Again, same profile with more oxidant doses, further increase in your Cl minus concentration. This is dosage number 2, right. And again the deep wells, similar case, more or less increasing concentrations of Cl minus, let us say, right. So that is what we observe out here, right. Again, we never look at only one indicator, typically we look at multiple indicators, let us say, right, because we want to be able to have great confidence in our particular process, let us say, or to say with greater confidence, let us say, that what I presumed would happen actually occurred, let us say, right. So I am going to look at multiple indicators here, and one of the such indicators is the byproduct here, which is Cl minus, let us say, right. So let us move on. So one other aspect is obviously, as we mentioned earlier, Fe2 plus is present in the relevant soil, and that will be oxidized by MnO4 minus. So now let us look at the data. So before injection of MnO4 minus, let us look at what the status was. So in the shallow regions, considerable iron, and in the deeper regions, again considerable amount of ferrous iron present, right. And this is something that we did look at earlier, let us say, right. So that is something to keep in mind, right. We have considerable levels of ferrous iron, let us say. So after addition, what would we typically presume? We would presume that it would decrease, and that is what you see out here in the shallow region and even in the deeper region. So it is relatively decreased now, let us say, right, relatively decreased if you can compare the relevant data. This is in the shallow and the deeper wells, let us see, right. So again, there should be further decrease typically. Again, that is what you observe here, as you now see, right, there is a decrease or further decrease in Fe2 plus, right. And after the third injection and final injection, right, most of the Fe2 plus seems to have been converted to Fe3 plus, let us say, right. Here they looks like they specifically looked at Fe2 plus, let us say, right. And one other aspect to keep in mind, that Fe2 plus is relatively soluble or will be present or can be present at higher concentrations in water, let us say, but Fe3 plus is typically insoluble, okay, and depending upon the pH, let us say, it typically precipitates out let us say, right, typically in this form, let us say, right. Again, different ligands, and it can also precipitate out probably in different forms, but this is one form that Fe3 plus can precipitate out, let us say, right. So Fe2 plus, if you add an oxidant, let us say, or if it is oxidized to Fe3 plus typically precipitates out, and very little Fe3 plus will be present in the relevant groundwater, let us see. Again, so this is again, as you can see, the concentration of Fe2 plus has considerably decreased, and this is in line with what we expected based on the MnO4 minus addition, which is a strong oxidant, let us say, right. So let us move on. Again, methane, let us see, right, typical in reducing conditions. So in pre-oxidation, this is what we have in what do we say, in the shallow wells and the deep wells here, shallow wells to the left here, right. And post oxidation, you see decrease. So CH4 is what we had earlier. So if there was complete oxidation, CH4 could have been transformed into or been oxidized into CO2 by what now? By the oxidant that you are adding, let us say MnO4 minus plus CH4, let us say, or MnO4 minus would oxidize methane into CO2, let us say, if the complete degradation did occur, let us say, or that is one particular possibility anyway, right. So, as you see the methane concentrations typically decreased, yes. So, let us move on. So, now we are also going to look at some other cases, but only in post oxidation after the injection of or the third injection, let us say, of the oxidant, and these are aspects that are important because sometimes while adding your particular oxidant you can have some or come across some scenarios which you did not foresee, let us say, right. Let us look at this particular case as in chromium concentration, right. So, chromium, let us say, so here we do not have which oxidation state it is, but typically chromium is present in water at relatively high concentration only when it is in +6, because chromium in oxidation state 3 is typically insoluble and will precipitate out, let us say. So, this is typically insoluble, chromium in oxidation state 3 is insoluble and only in oxidation state 6 is relatively soluble, let us say, right. So, let us look at this particular case again. We do not have the data for the pre-oxidation case, let us say, or data for chromium concentration in the groundwater, let us say, or subsurface before addition of MnO4 minus. Anyway, that was not presented, let us say, but let us look at one scenario here, right. So, let us say you have chromium 3, let us say, in the relevant soil or relevant soil, let us say, right, and then you are adding manganese or permanganate, pardon me, or which is an oxidant. So, what can happen? Chromium which was in the oxidation state 3 and which was insoluble, let us say, or relatively present at very low concentrations in the groundwater will now be transformed by MnO4 minus, which is an oxidant, to chromium 6, right. So, which is relatively much more soluble and thus relatively higher concentration in the groundwater. What does that mean? Now, the chromium concentration or chromium can be transported over a wider area, let us say. So, that looks like that is one possible case, but obviously we do not have the pre-oxidation data here. This is only from the post-oxidation after the third injection, let us say, right. You see considerably high concentrations of chromium here, right, and that typically would have been chromium 6, and so that is one unintended, let us say, consequence of addition of your particular oxidant, let us say, right. A compound, a toxic compound which was relatively immobile earlier is now relatively more mobile, let us say, right. That is chromium out here. And let us look at the other case. So, ORP, so it is the potential here, right. Again, keep in mind this is post oxidation after the third injection. So, earlier it would have been typically reducing conditions, and I think we looked at some brief data there earlier, if not the graph, but after you add considerable amount of oxidant doses, what is going to happen now? Obviously, you are going to have oxidizing conditions present, right, and so that is what you see here as in minus typically reducing conditions, and here what does this mean? As you go higher up, it means that oxidizing conditions prevail, let us say, right, oxidizing conditions prevail, and that is what you see here after the third injection. The subsurface, how is it now? It is such that the potential is typically in the oxidizing conditions, let us say. So, that is something that you see, and again obviously that is expected, right. You are adding a lot of what do you say, oxidant out here, right. So, that is something to keep in mind, right. But one particular data again based on the stoichiometry, let us say, right, as we know is a general ORP is a general indicator of oxidizing conditions in the subsurface, right. One aspect I want to point out here is that earlier we had PCE and that was degraded to TCE, then DCE and then VC, right. This is one order that can occur, let us say, right. But when would this have occurred? Only when reducing conditions prevail, let us say. But for reducing conditions to prevail, what should not be present? Certainly not oxygen, typically not even nitrate, not even Fe3 plus, let us say. What are all these? All these are electron acceptors, let us say, right. If all these electron acceptors are present, let us say, this particular process would not take place. Why is that? Because this is also an electron acceptor, right, and the microbes would have degraded it in this way, right, as in this order, PCE going to TCE going to DC and VC, only if all these what do we say, compounds, let us say, that we have out here are not present. Why is that? Because if they are present, the microbes would not have used PCE as the electron acceptor, they would have used oxygen as the electron acceptor or nitrate as the electron acceptor, right. So, if the relevant PCE was degraded into the byproducts, what does that mean? Typically it would have meant that earlier reducing conditions were prevailing and also that all these competing electron acceptors were not present, right. So, that is something to keep in mind. So, pre-oxidation arsenic concentration, so looks like they had arsenic, right, remarkably toxic and carcinogenic compound arsenic, right, and post oxidation, let us say similar, we also call it in deep aquifer, as in this is I believe from shallow wells, but what we say is that even in the deep aquifer we have considerable concentrations of arsenic, or rather we had considerable concentration of arsenic, let us say, right. So, it looks like there were some local sources of arsenic, let us say, typically arsenic is also present subsurface, typically, or depending upon the relevant site obviously, right. It can either be dumped, let us say, or due to some conditions, or it can also be present naturally in the subsurface. We do not know what the case is, but we do know that prior to adding the permanganate we do have arsenic in the relevant location, let us say, right. So, all groundwater samples in the deep region were reported as non-detect for arsenic. So, okay, I guess it was only present in the shallow regions and not in the deep regions, let us say, right. So, let us look at the case here after addition of your particular oxidation, let us say this is post oxidation 3 and 4, let us see. As you can see what is happening now, typically the arsenic concentration has decreased now. So, why is that, let us say, right. Arsenic can be present in different forms, arsenic I believe in oxidation 3, and if I am not wrong in arsenic in the form of oxidation state 5, let us say. But both these forms are relatively soluble now, right, as in no form is relatively more insoluble to my knowledge than the other. But why do we see a decrease, let us say, in this particular arsenic concentration, right. This is after post injection 3 I guess, and after 4, let us say, that is what they say here. And what was it earlier? So, you had earlier considerably high concentrations of arsenic, and the concentration of arsenic is decreasing now. So, why is that though, right. So, the reason here is that, or one probable reason is that, if you remember what is happening to the permanganate that we are adding MnO4 minus, it is taking in some electrons or accepting some electrons, and it would have been transformed into MnO2, the solid, let us say. Or we also know that Fe2 plus in this condition would have been oxidized to Fe3 plus, and while releasing an electron, and we know that Fe3 plus will not stay as Fe3 plus, but would precipitate out, let us say, right. So, we know that these solids can be formed now, right. So, what happens here is, as these particular solids precipitate out, let us say, arsenic will be adsorbed onto these particular solids that are precipitating out, and you will have something called co-precipitation, let us say, right. So, this is one mechanism by which, let us say, some of the heavy metals are going to be removed, and in this case I believe that is what happened with arsenic in this case, let us say, as in ferric iron and also manganese, let us say, after relevant reduction, let us say, ferric iron from ferrous, right, and then so we had Fe2 plus going to Fe3 plus, and then release of the relevant electrons, and MnO4 minus going to MnO2, the solid, right, and both these solids Fe3 plus with the I mean the one that precipitates out, and MnO2, let us say, while they are precipitating out, they can act as sites for adsorption of the relevant arsenic, let us say, and that is one very probable way, and again that is typically used out there too, right, as in to remove arsenic, and this is one probable way how arsenic concentration would have decreased. So, the planners might not have planned for it, but that is where one unintended benefit, let us say, right. So, these are some of the aspects to keep in mind. So, what are the conclusions here? Significant reduction obviously in CVOC, right, both in groundwater and soil, that is the key here. And how can we be sure? As you know that, let us say, if they injected it today, they looked at the monitoring after around 2 months, let us say, and I think around 6 months, and so on, let us say. So, any partitioning between the relevant soil and water, or the equilibrium would have been relatively reached, right. So, that is something to keep in mind. So, both the groundwater and soil were remediated. So, typically 92% and 76% reduction in total CVOC mass flux, right, as in at different wells, right, you have different wells, you will be able to calculate the flux as in mass that is being transported per area per time. So, now that has decreased considerably both in shallow to a greater region and also considerably in the deeper region, but not to such a great extent, right. And also, though this is what we talked about earlier, but looks like CVOC rebound was determined in 3 out of 38 wells, as in it is not as if there was no rebound or increase in the CVOC concentration. Again, how is this rebound going to occur now? So, let us say you have soil and the CVOC on the particular soil and groundwater here, you remove all the contaminant in the groundwater, some of the contaminant is going to change phase from the soil into the groundwater, right. So, thus you will observe rebound now. So, in most of the wells obviously no rebound was what do we say detected, but looks like some rebound was detected in 3 of the wells, and that could be the reason for, let us say, the deeper or the efficiency being relatively less in the deeper regions, let us say, right. So, that is one particular case. So, I guess we did look at one comprehensive what do we say case study here, and now we looked at a case where both the groundwater and soil were contaminated, let us say, with relatively more hydrophobic compounds. We went ahead with the chemical process, and we had some considerable benefits with respect to the primary contaminants, and then some unintended advantages and disadvantages in the sense that chromium was released while arsenic was removed, right. So, you understand that there are different aspects at play, right. So, I guess again I ran out of time, so I am going to end my session today, and that is it from me for today, and thank you.